Hello and welcome to Building for the Edge, Verizon 5G Edge and AWS Wavelength Foundations. My name is Robert Belson and I'm joined here with Kurt Campbell from our MEC Strategy and Architecture team. Over the course of the next 30 minutes, we're going to take you through the fundamentals, what you need to know about building your first application on AWS Wavelength and 5G Edge today. We're going to take you through those key building blocks, then jump right into the AWS console to show you how to build your first app. And then we'll leave you with some best practices and tips and tricks for performance benchmarking, IoT applications, and specifically how you would architect a production-grade application on EKS at the network edge. So to kick things off, what exactly is 5G Edge? So back in August, Verizon with AWS jointly announced our 5G Edge mobile edge computing solution on AWS Wavelength, where the AWS services that you know and love, such as EC2, ECS, and EKS, would be available at the edge of our 4G and 5G nationwide network. Today, we're excited to share that AWS Wavelength is available in 7 cities, and be on the lookout for even more cities to come. But for those of you who've yet to build on AWS Wavelength, let's start with the basics. Why deploy applications to the network edge altogether? To give you a great example of why, let's consider an e-commerce application. We see that over 100 milliseconds in delay or latency can hurt conversion rates by over 7%. And in the case of checkout speed, we see that checkout speed, which is often dependent on that end-to-end compute latency, remains one of the most important factors of whether a customer will return to a given site. So the question we as architects, as product owners, as developers often face is, how do we improve user experience? How do we improve conversion rates? But doing so without sacrificing the seamlessness of the tools our application teams leverage today. The solution is 5G Edge, made available today via AWS Wavelength. Not only do you get those key compute services in EC2, ECS, and EKS, not only do you get EBS for storage, not only do you get those key management functions in CloudWatch for monitoring, for CloudTrail, auto-scaling for infrastructure elasticity, CloudFormation for infrastructure as code, but we've gone ahead and tailored those services specifically to support our customers' needs for those mobile immersive experiences. Let me give you a great example. EC2 today, in wavelength zones, supports that G4 family instance type, which allows developers to leverage the power of NVIDIA T4 GPUs at the network edge for augmented reality, computer vision, machine learning, and so much more. We're seeing so many great use cases from our customers today, but we're so excited to see what you are going to build at the network edge. But let's start with the fundamentals here. What's different about AWS Wavelength than what I might expect in the parent region, in what I would expect in AWS today? First and foremost, we got to start with that VPC. That's the baseline for all of your cloud infrastructure. That doesn't change. But then, as you would today, if you were to add a new subnet corresponding to a particular availability zone, you instantiate a wavelength zone in precisely the same way, just selecting a wavelength zone corresponding to the edge of our mobile network in, say, Boston, in, say, Atlanta, in, say, the Bay Area. And then from there, by attaching a carrier gateway to your subnet and having the route table specify outbound traffic to go through that carrier gateway, you have in turn connected your infrastructure to our 4G and 5G nationwide network. What's so important about that is any resources instantiated therein are now part of that mobile edge computing fabric. From there, as you instantiate resources as you typically would, say for an EC2 instance, you need to attach what's called a carrier IP, which you might think of as analogous to the elastic IP. The carrier IP corresponds to specifically an IP address as part of a pool of IP addresses in the network border group corresponding to that wavelength zone. So the idea here is when you attach a carrier IP to a particular instance in a wavelength zone and have already attached that carrier gateway to the route table corresponding to that subnet, you've now built that fully resilient infrastructure that will connect your infrastructure to our mobile network. But the best way to show you this is to show it live in the AWS console. So let's jump right into it to learn more. So here we are in the AWS Management Console, and today we're going to launch our first EC2 instance in an AWS Wavelength zone. And today we're going to launch specifically in the Bay Area San Francisco Wavelength zone. Before we get started, we want to make sure that we have access to wavelength zones, and the way we do that is we go to the EC2 section of the console, and under Account Attributes, go to Zones, and we'll see that just as we have all of these availability zones in the parent region available to us, we'll also see a green check mark next to the Bay Area wavelength zone if, in fact, wavelength zones is enabled for your account. If it's not, you may see a red check that says disabled, and you'll just click the button right here. But assuming you have access, let's jump right in and get started. So we're going to go to VPC, and we're going to create a new VPC for the wavelength zone to live in. So we're going to go down to VPCs here, then we're going to create a VPC. Let's call it My Awesome VPC and just use the CIDR range that AWS provides for us as a recommendation. Then we click Create VPC and we are good to go. Now what we need to do is go to Carrier Gateways as a section within the VPC console. Click on Carrier Gateways and create a Carrier Gateway. Remember, this is how those mobile devices connected to our 4G and 5G network access the wavelength zone. So let's call this My Carrier Gateway. We have to attach it to our VPC that we just created, My Awesome VPC. And then by clicking this checkbox right here, once we create a subnet, we then attach the Carrier Gateway to the route table associated with that subnet. So now we're going to go ahead and add a subnet. Let's call this My Bay Area Wavelength Zone. And then we'll select, of all of the wavelength zones available in this drop-down menu at any given point in time, that here we have the Bay Area Wavelength Zone. And then we just need to make sure that the CIDR range here is a subset of that of the VPC. Let's do 10.0.0.0/26. Great. We've done that. We've routed the subnet traffic to the Carrier Gateway, and we are good to go. We'll see here that just from the console here, we've automated a bunch of different steps, and we can see, as an example, beyond the default subnets associated with the default VPC, we go down here to My Bay Area Wavelength Zone. Look what happened in the route table. Not only was the local route created for all traffic within the VPC, within a subnet in a wavelength zone, or otherwise, can seamlessly connect by way of private IP, but also for traffic destined to the internet, what it's saying here is go through that Carrier Gateway with the ID of the Carrier Gateway noted here. So we're almost done here with that infrastructure to get started. One more thing we want to do. We want to go down to elastic IPs. We mentioned that one of the key building blocks for wavelength zone infrastructure is that carrier IP. And you do so through the elastic IP section of the console. So let's allocate a carrier IP. Under network border group, it's very important that we change this to the wavelength zone here. So what this is doing is, again, we're reserving an IP address within that pool of addresses associated with that Bay Area wavelength zone so that we can attach it to instances in that wavelength zone so that it has connectivity to our 4G and 5G networks. So not only do you need the carrier gateway, you need the carrier IP associated with any EC2 instance. So let's go ahead and allocate that carrier IP. And again, you're going to see here that this is both this section of the console for elastic IPs and carrier IPs. And you're going to see here that this is of type carrier IP, this 155.146. So now again, we have the wavelength zone subnet that we created. We have the carrier gateway attached as a route to that subnet. We also have the carrier IP. All that's left to do, let's launch that EC2 instance. So we'll go to the EC2 section again, and we'll go ahead to running instances. There are none today. Let's go ahead and click Launch Instances. For the AMI, you could choose anything here. I'm just going to choose Amazon Linux 2. And then this is really important. You want to make sure here that if I were to select T2 Micro right now, that T2 Micro is not supported in a wavelength zone today. So you want to make sure to refer to the latest availability for AWS wavelength zones to make sure that you've selected an instance type that's supported. So I'm going to go ahead and select a T3 medium instance here. And then when I configure the instance details, beyond the number of instances I want to run, I have to remember to go to My Awesome VPC to launch that EC2 instance in this VPC and in turn in the Bay Area wavelength zone. From there, you can scroll down to IAM role. I'm going to go ahead and select the SSM role. This is really important because remember that if I wanted to SSH into this instance, traffic from the broader internet is blocked. So I have two options. I could use a Bastion host, or I could SSH in from my phone, neither of which are desirable to me. So what I'm going to use is the session manager agent so that I can seamlessly, effectively SSH in from my console. And so this is a little trick here for IAM roles. Next, we're good to go. We can go to review and launch. Again, it's going to ask us for a key pair. We're not going to use it, but we're going to click the I acknowledge checkbox and then go ahead and launch our instance. So this is everything you need as you go to the running instances here in the console. You now have your first instance running, as you can see here, in the availability zone. All you need to do is now go back to the Elastic IP subsection, go to associate Elastic IP address. And what we're doing is we're associating this carrier IP to the running EC2 instance we just created. And this is what's fascinating. If we go back to the EC2 dashboard, or rather the instances section, we'll see under instance attributes, soon the Elastic IP will show up right here. And now you see it. So that, folks, is how you launch your first EC2 instance in a wavelength zone. And let's get back to some best practices for how to measure your application on 5G Edge. So before we jump into some of those best practices, let me show you a great example of 5G Edge in action. What you're seeing here on the screen is we're sending a live stream of a millisecond clock from a camera, from a mobile phone's camera, to a wavelength zone and to an availability zone in that parent region for media encoding, packaging, and delivery back to that same device. And so what we're trying to do here is if you overlay that original video source on top of that playback stream, you can actually see the difference in end-to-end latency. And so check this out. If we're comparing that difference in millisecond clocks, both for that deployment, as I mentioned before, to the wavelength zone and then deployment in the region, that's one way you can measure and benchmark performance, that apples-to-apples comparison that we'll see in a few slides. If you look at that difference, what you're going to see is almost 1,000 milliseconds. That's a full second. That could be the difference between watching the game-winning touchdown live versus getting a tweet about it just prior. That's the transformative nature and the value proposition that 5G Edge provides developers today. But we wouldn't be here today without talking about 5G, one of the most transformative networking technologies to date. And one of the questions we continue to get from developers is, why does 5G matter to me? Let me turn it over to Kirk to tell us a little bit more. Kirk, take it away.
Augmenting performance of edge computing with 5G. We at Verizon have been working tirelessly in architecting and deploying our 5G network. Some of the assets that we're adding to the infrastructure with our partners at Amazon are a multi-access edge computing platform called Wavelength. We're adding software-defined network capability. We've invested heavily in millimeter wave spectrum, and we've deployed deep fiber assets to support the bandwidth needs of this revolutionary technology. So what are some of the currencies that developers will be able to take advantage of as a result of 5G? You'll have ultra-low latency, much higher data rates, much higher data volumes, and hundreds to thousands of more devices to support the journey to the IoT, and much longer battery life. What are some of those best characteristics when it comes to the 5G Edge and Wavelength platform? You'll have much lower latency, but even more importantly, you'll have much higher throughput, much higher downlink, as well as uplink throughputs. With that much higher bandwidth, you'll be able to move your images for your computer vision applications and your inference use cases so that you can recognize real-time improvements with these types of services at the edge. How do you measure performance of your 5G Edge application? Many of us use ICMP as a way to measure latency. But ICMP was conceived as a network troubleshooting tool, not a performance tool. Again, it was designed to to measure availability, not performance. For that reason, we definitely can't use this to measure performance because even gateway routers deprioritize ICMP packets. So what are some better alternatives? We can use HTTP stat, where we actually have real application traffic instead of a static payload. We also get that three-way TCP handshake. We can use tools like iPerf3, which can give you TCP and UDP testability so that you can measure throughput, jitter, and loss. And then once you've deployed these tools, we recommend that you do an apples-to-apples comparison between the wavelength 5G edge zone and the next best thing, the parent region. We wouldn't be telling the complete story here without talking to you about how you can build your 5G edge applications with our IoT platform in Verizon ThingSpace. Whether you're a Raspberry Pi developer or an industrial IoT engineer, we have devices that can seamlessly connect your IoT fleet to the 5G edge infrastructure. This enables opportunities for real-time data streaming and machine learning-based anomaly detection for equipment remediation and product integrity use cases. Beyond specific manufacturing and industrial use cases, IoT has the power to drive network intelligence across our cloud infrastructure. Today, the elasticity or the ability to scale up and down is often contingent upon metrics such as CPU utilization, memory, and network traffic. What if I said you don't need to wait until that threshold was triggered to cause a scaling activity? Instead, you can use ThingSpace Device Location API as a custom metric and create an Amazon CloudWatch alarm on this metric to scale your infrastructure. Leveraging techniques like this, our intelligent edge network can truly become an asset in your infrastructure deployments. We talked a lot about compute to edge, but what about distributed storage assets? Our teams have been hard at work to explore these challenges. Take our Verizon location technology team, building the next generation mapping capabilities with autonomous mobility and CVDX use cases. At the heart of all this is reverse geocoding, or where am I requests. By sharding their location database into geospecific map tiles, they extended their mapping functionality to the network edge for an ultralight implementation of the capability. We're excited to invite one of our Verizon location technology architects, Mark Persico, to join us here today to tell us more about how his team has approached developing applications at the 5G edge with Kubernetes. More specifically, what are some tips and tricks that you would advise the other engineering teams as they build out their first app on EKS on the edge?
Thanks. My name is Mark Persico, and I'm really excited to share the 5G Edge solution I've architected for Verizon Location Technology. Our motivation to use EKS in 5G Edge was to standardize our application and infrastructure strategy at the edge. EKS allows us to use a managed Kubernetes service to deploy, run, and scale applications in the same manner. Extending EKS to 5G Edge meant those applications can take advantage of Verizon's MEC footprint for latency-sensitive operations and locally relevant data. In order to extend EKS to 5G Edge and extend our ability to deploy applications to 5G Edge, we undertook a four-phased approach: building the edge infrastructure for EKS and overcoming challenges there, architecting our application and data for 5G Edge, deploying our application to EKS on 5G Edge, and connecting our application to the Verizon network. I will walk through each phase in turn.
So I am showing you a screen here now with our Kubernetes infrastructure as it existed before 5G Edge. So the first step would be to build the edge infrastructure. And then after that, architect application data for 5G Edge, both the application and the data. And then doing the deployment to 5G Edge and connecting it to the Verizon wireless network. So as I said before, we started with our existing cluster. We have the availability zone 1 and availability zone 2. I'm just circling here. Now, 2 availability zones are important with their worker nodes in private subnets. We also have some in public subnets for cloud-based ingress. Separate availability zones give fault tolerance, especially important for Verizon location of an edge service, 5G Edge, because it has to be able to talk back to the parent region, and you wouldn't want only one zone in the parent region to talk to for fault tolerance. So with that, we also extended to wavelength. Finally, in this case, it was the Chicago pilot zone. So we built a wavelength zone components of carrier subnet and route table and a private subnet and route table, the purpose of which was to isolate carrier traffic from traffic that we wouldn't want to go to the private subnet at all. We're interested in application traffic getting through here, but we needed to protect the node workers themselves, the worker nodes, so that we only serve sanctioned application traffic back to them. Now, we launched an unmanaged EKS node group here. EKS, the control plane must run version 117 or higher or later. Normally you have the ability in EKS to use a managed node group, but that's not possible in Wavelength, so we had an unmanaged node group in place there with our own automation. Additionally, we had to set up endpoints for AWS to advertise certain services like Ec2 or Elastic Container Registry out to the Wavelength zone for the worker nodes to pick up images or talk back to Ec2 services, such as the Kubernetes API server. And here again, that's where having multiple availability zones in the region helps. We launched an unmanaged node group, as I said before. We also have an S3 gateway endpoint to optimize traffic from those worker nodes back to an S3 bucket in the parent region where certain services within EKS would depend on it. Now, in addition to the infrastructure, it's important we label it for deployment. So here we are with our node labels. Labels are a powerful concept in Kubernetes that lets you select where applications go based on compute attributes of the nodes. Here, it's just the placement equals edge label. We chose to use also subnet choice private, as you can see. We then we have a node selector in the application that deploys an application to this node based on those node labels. So finally, there's no ELB types in Wavelength, so we have this edge proxy ASG sitting in the carrier subnet and connected to our carrier route table. Now, for the data and the application itself, it's important to remember that you don't want to put your entire application or data set on 5G Edge. You only want the parts that are locally significant or require the low latency compute capabilities that MEC provide. And compute and storage resources, remember, are more limited in an edge location than at the scale of the cloud. So consider the functions of your applications that would benefit from running in low latency compute. Which ones are latency sensitive and which ones aren't? Also consider the data upon which those functions depend. Partitioning application for the edge is as important as deploying the application to the edge. As I said, don't put your entire data set for the application on the MEC environment. And here's a really good example. It's the multi-access edge compute based reverse geocoder. Reverse geocoding means turning a latitude-longitude pair into a street address. In this application, which runs on our mobile devices at Verizon Location Technology, we are able to click on a point in this bounding box, and it illustrates the difference between what a request for the address would look like from the local data in the MEC node, 150 milliseconds for the MEC node, 370 milliseconds for the cloud. And so here you can see the advantage of MEC is providing much lower latency for local data. Contrast that to a call outside of the MEC coverage area, then it actually came back at 179 milliseconds, but it made that cloud round trip all the way out past where it needed to go because the data was not in MEC. Now, we did a fixed data set partition of data in this MEC coverage area, but that's easy to do. Dynamically updating this map with new information for mobile applications requires a good synchronization mechanism. Caching that data from the cloud also requires a synchronization mechanism. This is just a purpose of illustrating how to partition data when you're dealing with a fixed data set, such as this that's locally relevant. So when it comes to deploying the app itself, these blue symbols would illustrate that we use an ingress as a single point of entry for applications. That's a neat Kubernetes feature. That ingress can't talk directly to named services in the cluster. It has to talk to a node port service because the ingress is looking for like names of services, but for the Edge proxy to reach them, the node port exposes actually a high-level TCP port on the EKS worker node, and that is how we bridge the gap from the carrier back to the applications on EKS.
In conclusion, the location-based value of 5G Edge is that it gives application users the opportunity to see locally relevant application data and engage meaningfully with it, with less latency than that of cloud-based applications. Lower latency ultimately means that users, whether they are human or machine, will be able to understand the world around them even more quickly and answer questions like, where am I and what's around me? And how do I adapt to my environment in real time? A 5G world will place increased importance and demand on contextually aware machines and software, in turn establishing location technology as a necessary component for the 5G future. Thank you for listening, and now I'll turn it over to Robbie and Kirk.
Thanks, Mark. And there you have it, folks, the fundamentals of 5G Edge and AWS Wavelength. And so to close out here, whether you're a product owner, a DevOps engineer, or an owner of an application team, there's definitely something in 5G Edge for you. Whether you're trying to boost performance of an existing application or designing a greenfield application for mobile immersive experiences, we want to be your trusted partner in building your next digital transformation with 5G and Verizon 5G Edge.
You can go to verizon.com/5G Edge to learn more about how to get building on the 5G Edge, and be sure to check out our 5G Edge blog for latest product updates, tutorials, and reflections from our customers and the broader developer community. So on behalf of the 5G Edge team, thank you for joining, stay safe, and enjoy the rest of reInvent.